Hey, genuine well wishes and constructives. I presume you and your beloved ones are fine and dandy. It is social activist, some good-hearted preacher, Professor S. back with altruistic delight for my 97th video on Anvil of publication on YouTube today, 18th October 2020, Sunday. Topic for discussion today is reliability and safety engineering. Reliability may be defined in several ways. The idea that something is fit for purpose with respect to time, the capacity of a device or system to perform as designed, the resistance to failure of a device or system, the ability of a system or device to perform a required function under stated conditions for a specified period of time, the probability that a functional unit will perform its required function for a specified interval under stated condition, the ability of something to fail without catastrophic consequences. Reliability engineers rely heavily on statistics, probability theory, and reliability theory. Many engineering techniques are used in reliability engineering, such as reliability prediction, table analysis, thermal management, reliability testing, and accelerated life testing. Plus, a large number of reliability techniques that expense on the varying degrees of reliability required for different situations. Most projects develop a reliability program plan to specify the reliability tasks that will be performed for the specific system. The function of reliability engineering is to develop the reliability requirements for the product, establish an adequate reliability program, and perform appropriate analysis and tasks to ensure the product will meet its requirements. These tasks are managed by a reliability engineer who usually holds an accredited engineering degree and has additional reliability specific education and other fields such as security engineering can also be approached using reliability engineering techniques. Many types of engineering employ reliability engineers and use the tools and methodology of reliability engineering. For example, system engineers design complex systems having a specified reliability. Mechanical engineering engineers may have to design a machine or system with a specified reliability. Automotive engineers have reliability requirements for the automobiles and components which they design. Electronic engineers must design and test the products for reliability requirements. In software engineering and systems engineering, reliability engineering is a sub-discipline of ensuring that a system or device in general will perform its intended functions when operating in a specified manner for a specified length of time. Reliability engineering is performed throughout the entire life cycle of a system, including development, test, production, and operation. Reliability engineering is concerned with four elements. First, reliability is a probability. This means that failure is regarded as a random phenomenon. It is recurring event, and we do not express any information on individual failures. The causes of failures are relationships between failures, except that the likelihood of failures to occur varies over time according to the given probability function. Reliability engineering is concerned with meeting the specified probability of success at a specified statistical confidence level. Second, reliability is predicted on intended function, generally that is taken to mean operation without failure. However, even if no individual part of a system fails, but the system as a whole does not do what was intended, then it is still charged under the system reliability. The system requirements specification is a criterion against which reliability is measured. Third, reliability applies to a specified period of time. In practical terms, this means that the system has a specified chance that it will operate without failure before time. Reliability engineering ensures that components and materials will meet the requirements during the specified time. Units other than time may sometimes be used. The automotive industry might specify reliability in terms of distance traveled. Military might specify reliability of a gun or a specified number of rounds fired. A piece of mechanical engineering may have a reliability rating value in terms of cycles of use. Excuse me. Fourth, reliability is restricted to operation under stated conditions. This constraint is necessary because it is impossible to design a system for unlimited conditions. The Mars rover will have different specified conditions in the family car. The operating environment must be addressed during design and testing. Many tasks, methods, and tools can be used to achieve reliability. Every system requires a different level of reliability. A commercial airliner must operate under a wide range of conditions. The consequences of failure are great, but there is a correspondingly higher insignificant consequences of failure, much lower budget. The reliability program plan is used to document exactly what tasks, methods, tools, analysis, and tests are required for a particular system. For complex systems, the reliability program plan is a separate document. For simple systems, it may be combined with the systems engineering management plan or integrated logistics support management plan. The reliability program plan is essential for a successful reliability program and is developed early during system development. It specifies not only what the reliability engineer does, but also the tasks performed by others. The reliability program plan is approved by a test by top program management. For any system, one of the first tasks of reliability engineering is to adequately specify the reliability requirements. Reliability requirements address the system itself, test and assessment requirements, and associated tasks and documentation. Reliability requirements are included in the appropriate system subsystem requirements, specification, test plans, and contract statements. Requirements are specified using reliability parameters. The most common reliability parameter is the mean time between failures, MTBF, which can also be specified as a failure rate or the number of failures during a given period. These parameters are very useful for systems that are operated on a regular basis, such as most vehicles, machinery, and electronic equipment. Reliability increases as the MTBF increases. The MTBF is usually specified in hours, but can also be used with other units of measurement, such as miles or cycles. In other cases, reliability is specified as a probability of mission success. For example, reliability of a scheduled aircraft flight can be specified as a dimensionless probability or a possibility. A special case of mission success is a single shot device or system. These are devices or systems that remain relatively dormant and only operate once. Examples include automobile airbags, thermal batteries, and missiles. Single shot reliability is specified as a probability of success or is subsumed into a related parameter. Single shot missile reliability may be incorporated into a requirement for the probability of a hit. For such systems, the probability of failure on demand, PFD, is a reliability measure. This PFD is derived from failure rate and mission time for non-repairable systems. Repair is not a correct term. Service, we should say. Repair means the opposite, really. For repairable systems, it is uptime from failure rate and mean time to repair, MTTR, and test interval. This measure may not be unique for a given system, as this measure depends on the kind of demand. In addition to system level requirements, reliability requirements may be specified for critical subsystems. In all cases, reliability parameters are specified with appropriate statistical confidence intervals. Reliability modeling is a process of predicting or understanding the reliability of a component or system. Two separate fields of investigation are common. The physics of failure approach uses an understanding of the failure mechanisms involved, such as crack propagation or chemical corrosion. The parts stress modeling approach is an empirical method for prediction based on counting the number and type of components of the system and the stress they undergo during operation. For systems with a clearly defined failure time, it is sometimes not given. For systems with a drifting parameter, the empirical distribution function of these failure times can be determined. This is done in general in an accelerated experiment with increased stress. These experiments may be divided into two main categories. Early failure rate studies determine the distribution with a decreasing failure rate over the first part of the bathtub curve. Here, in general, only moderate stress is necessary. The stress is applied for a limited period of time in what is called a sensor test. Therefore, only part of the distribution with early failures can be determined. In so-called zero defect experiments, ZD, which is the main concept in TKR, only limited information about the failure distribution is required. Here, the stress time or the sample size is so low that not a single failure occurs. Due to insufficient sample size, only an upper limit of the early failure rate can be determined. At any rate, it looks good for the customer if there are no failures. In a study of the intrinsic failure distribution, which is often a material property, a higher stresses are necessary to get failure in a reasonable period of time. Several degrees of stress have to be applied to determine an acceleration model. The empirical failure distribution is often parametrical with a variable or a log normal model. It is general practice to model the early failure rate with an exponential distribution. This less complex model for the failure distribution has only one parameter, constant failure rate. In such cases, the chi-square distribution can be used to find the goodness of it for the estimated failure rate. Compared to a model with a decreasing failure rate, this is quite pessimistic. Combined with a zero defect experiment, this becomes even more pessimistic. The effort is greatly reduced in this case. One does not have to determine a second model parameter, that is the shape parameter of a variable reliability probability density function for its confidence interval. Example, by a maximum likelihood approach, the sample size is much smaller because reliability is a probability. Even highly reliable systems have some chance of failure. However, testing reliability requirements is problematic for several reasons. A single test is insufficient to generate enough statistical data. Multiple tests or long duration tests are usually more expensive. Some tests are more simply impractical. Reliability engineering is used to design a reliable and affordable test program that provides enough evidence that the system meets its requirements. Statistical confidence levels are used to address some of these out concerns. A certain parameter is expressed along with a corresponding confidence level. For example, an MTBF of 1000 hours and 90% confidence at 90% confidence level. For this specification, the reliability engineer can design a test with explicit criteria for the number of hours and the number of failures until the requirement is met or failed. The combination of reliability parameter value and the confidence level greatly affects the development cost and the risk to both the customer and the producer. Care is needed to select the best combination of requirements. Reliability testing may be performed at various levels such as components, subsystems, and system. Also, many factors must be addressed during testing such as extreme temperature and humidity, shock, vibration, and heat. Reliability engineering determines an effective test strategy so that all parts are exercised in relative environments for systems that must last for many years. Reliability engineering may be used to design an accelerated life test. Reliability engineering must also address requirements for various reliability tasks and documentation using system development, test production, and operation. These requirements are generally specified in the contract statement of work and depend on how much leeway the customer wishes to provide to the contractor. Reliability tasks includes various analysis, planning, and failure reporting. Task selection depends on the criticality of the system as well as cost. A critical system may require formal failure reporting and review process through development, whereas non-critical system may rely on final test reports. The most common reliability program tasks are documented in reliability program standards such as MIL HTB 785, IEEE 1332. Failure reporting analysis and corrective action systems are a common approach for a product process. Reliability monitoring, design for reliability, is an emerging discipline that refers to the process of designing reliability into products. This process encompasses several tools and practices and describes the order of the deployment that an organization needs to have in place in order to drive reliability for the products. Typically, the first step in the DFR process is to set the system's reliability requirements, targets. Reliability must be designed into the system. During system design, the top level reliability requirements are often allocated to subsystems by design engineers and reliability engineers working together as a team. Reliability design begins with the development of a model. Reliability models use block diagrams and fault trees to provide a graphical means of evaluating the relationships between different parts of the system. These models incorporate predictions based on parts count failure rates taken from historical data. While the predictions are often not accurate in an absolute sense, they are valuable to assess relative differences in design alternatives. One of the most important design techniques is redundancy. This means that if one part of the system fails, there is an alternate success path, such as a backup system. Contingency. An automobile brake light might use two light bulbs. If one light bulb fails, the brake light still operates using the other bulb. LED is a good option. You know, it is not just one LED, it's a set of LEDs. I would say a bank of LEDs. Redundancy significantly increases system reliability and is often the only viable means of doing so. However, redundancy is difficult and expensive and is therefore limited to critical parts of the system. Another design technique, physics of failure, relies, relies on understanding the physical process of stress, strength, and failure at a very detailed level. Then the material or component can be redesigned to reduce the probability of failure. Another common design technique is component derating. Selecting components whose tolerance significantly exceeds expected stress, or using a heavier gauge wire that exceeds the normal specification for the expected electrical current. It is over designing. They used to say Russian products are over designed generally. Many tasks, techniques, and analysis are specific to particular industries and applications. Commonly, these include built-in test, bit, failure mode and effects analysis, FMEA, reliability simulation modeling, thermal analysis, reliability block diagram analysis, fault tree analysis, root cause analysis, sneak circuit analysis, accelerated testing, reliability growth analysis, variable analysis, electromagnetic analysis, statistical interference, avoid single point of failure. Results are presented during the system design reviews and logistics reviews. Reliability is not just one requirement among many system requirements. Engineering trade studies are used to determine the optimum balance between reliability and other requirements and constraints. The purpose of reliability testing is to discover potential problems in the design as early as possible and ultimately provide confidence that the system meets its reliability requirements. Reliability testing may be performed at several levels. Complex systems may be tested at component, circuit board, unit, assembly, subsystem, and system levels. The test level nomenclature varies among applications. For example, performing environmental stress screening tests at lower levels such as piece parts or small assemblies catches problems before they cause failures at higher levels. Testing proceeds during each level of integration through full-up systems testing, developmental testing, and operational testing, thereby reducing program risk. System reliability is calculated at each test level. Reliability growth techniques and failure reporting, analysis, and corrective action system, active systems, FRACAS, FRACAS, are often employed to improve reliability as testing progresses. The drawbacks to such extensive testing are time and expense. Customers may choose to accept more risk by eliminating some or all levels or all lower levels of testing. It is not always feasible to test all system requirements. Some systems are prohibitively expensive to test. Some failure modes may take years to observe. Some complex interactions result in a high number of possible test cases, and some tests require the use of limited test ranges or other resources. In such cases, different approaches of testing can be used, such as accelerated life testing, design of experiments, and simulations. The desired level of statistical confidence also plays an important role in reliability testing. Statistical confidence is increased by increasing either the test time or number of items tested. Reliability test plans are designed to achieve the specified reliability at the specified confidence level with the minimum number of test units and test time. Different test plans result in different levels of risk to the producer and consumer. The desired reliability, statistical confidence, and risk levels for each side influence the ultimate test plan. Good test requirements ensure that the customer and developer agree in advance on how reliability requirements will be tested. The key aspect of reliability testing is to define failure or breakdown. Although this may seem obvious, there are many situations where it is not clear whether a failure is really the fault of the system. Variations in test conditions, operator differences, weather, and unexpected situations create differences between the customer and the system developer. One strategy is to address this issue to use a scoring confidence process. The scoring conference includes representatives from the customer, the developer, the test organization, the reliability organization, and sometimes independent observers. The scoring conference process is defined in the statement of work. Each test case is considered by the group and scored as a success or failure. This scoring is the official result used by reliability engineer. As part of the requirements phase, the reliability engineer must develop a test strategy with the customer. The test strategy makes trade-offs between the needs of the reliability organization, which wants as much data as possible, and constraints such as cost, schedule, and available resources. Test plans and procedures are developed for each reliability test, and results are documented in official reports. The purpose of accelerated life testing is to induce field failure in the laboratory at a much faster rate by providing a harsher but nonetheless representative environment. In such a test, the product is expected to fail in the lab just as it would have failed in the field, but in much less time. The main objective of an accelerated test is either of the following: to discover failure modes, to predict the normal field life from the high stress lab life. An accelerated testing program can be broken down into the following steps: define objective and scope of the test, collect required information about the product, identify the stress, determine level of stress, conduct the accelerated test, and analyze the accelerated data. Common ways to determine the life stress relationship are Arrhenius model, Airing model, inverse power law model, temperature humidity model, temperature non-thermal model. After a system is produced, reliability engineering monitors, assesses, and corrects deficiencies. Monitoring includes electronic and visual surveillance of critical parameters identified during the faulty analysis design stage. The data is constantly analyzed using statistical techniques such as variable analysis and linear progression to ensure the system reliability meets requirements. Reliability data and estimates are only key inputs for system logistics. Data collection is highly dependent on the nature of the system. Most large organizations have quality control groups that collect failure data on vehicles, equipment, and machinery. Consumer product failures are often tracked by the number of returns. For systems in dormant storage or on standby, it is necessary to establish a formal surveillance program to inspect and test random samples. Any changes to the system, such as field upgrades or recall repairs, require additional reliability testing to ensure the reliability of the modifications. Since it is not possible to anticipate all the failure modes of a given system, especially ones with a human element, failures will occur. The reliability program also includes a systematic root cause analysis that identifies the causal relationships involved in the failure, such that effective corrective actions may be implemented. When possible, system failures and corrective actions are reported to the reliability engineering organization. One of the common methods for reliability operational assessment is a FRACAS. It's a systematic approach for reliability, safety, and logistics assessment based on failure, incident reporting, management analysis, and corrective preventive actions. Organizations today are adapting this method and utilize commercial systems such as a web-based FRACAS application, enabling an organization to create a failure incident data repository from which statistics can be derived to view accurate and genuine reliability, safety, and quality performance. So when we see the quality is high, the reliability will be high. Some of the common outputs from a FACA system includes field MTBF, MTTR, spares consumption, reliability growth, failures, instance, distribution by type, location, part number, serial number, symptom, etc. The American Society for Quality, ASQ, has a program to become a certified reliability engineer, CRE. Certification is based on education, experience, and certification tests. Periodic recertification is required. The body of knowledge of the test includes reliability management, design evaluation, product safety, statistical tools, design and development, modeling, reliability testing, collecting and using data, etc. Another highly respected certification program is the Certified Reliability Professional, CRP. To achieve certification, candidates must complete a series of courses focused on important reliability engineering topics, successfully apply the learned body of knowledge in the workplace, and publicly present this expertise in an industry conference or journal. Reliability, availability, and maintainability, shortly RAM, are three system attributes that are of tremendous interest to system engineers, logisticians, and users. Collectively, they affect economic life cycle costs of the system and its utility. The origins of contemporary reliability engineering can be traced to the Second World War, after which Japan developed a lot drastically. The discipline's first concerns were electronic and mechanical components. However, current trends point a dramatic rise in the number of industrial, military, and consumer products with integrated computing functions. Because of the rapidly increasing integration of computers into products and systems used by consumers, industry, governments, and the military, reliability must consider both hardware and software. Maintainability models present some interesting challenges. The time to repair an item service is a sum of the time required for evacuation, diagnosis, assembly of resources, repair, inspection, and return. Administrative delay, such as holidays, can also affect repair times. Often these processes have a minimum time to complete that is not zero, resulting in the distribution used to model maintainability having a threshold parameter. The threshold parameter is defined as a minimum probable time to repair. The estimation of maintainability can be further complicated by queuing effects, resulting in times to repair that are not independent. This dependency frequently makes analytical solution of problems involving maintainability impracticable and promotes the use of simulation to support analysis. Maintainability is defined as a probability that a system element can be repaired in a defined environment within a specified period of time. Increased maintainability implies repair times, shorter repair times. Availability is defined as a probability that a repairable system or system element is operational at a given point in time under a given set of environmental conditions. Availability depends on reliability and maintainability. A failure is an events or inoperable state in which any item or part of an item does not or would not perform as specified. The failure mechanisms is a physical, chemical, electrical, thermal, or other process that results in failure. In computerized system, a software defect or fault can be the cause of failure, which may have been preceded by an error which was internal to the item. The failure mode is a way or the consequence of the mechanism through which an item fails. The severity of the failure mode is the magnitude of its impact. System designs based on user requirements and system design alternates can be formulated and evaluated. Reliability engineering during this phase seeks to increase system robustness, replacement through measures such as redundancy, diversity, built-in testing, advanced diagnostics, and modularity to enable rapid physical replacement. In addition, it may be possible to reduce failure rates through measures such as use of higher strength materials, increasing the quality components, moderating the extreme environmental conditions, or shorten maintenance, inspection, or overall intervals. Design analysis may include mechanical stress, corrosion, and radiation analysis for mechanical components, thermal analysis for mechanical and electrical components, and electromagnetic interference analysis (EMI), or measurements for electrical components and subsystems. In most computer-based systems, hardware mean time between failures are hundreds of thousands of hours, so that most system design measures to increase system reliability are focused on software. The most obvious way to improve software reliability is by improving its quality through more disciplined environmental development efforts and tests. However, reliability and availability can be increased through architectural redundancy, independence, and diversity. Redundancy must be accompanied by measures to ensure data consistency and manage failure detection and switchover. Within the software architecture, measures such as watchdog timers, flow control, data integrity checks, example hashing or cyclic redundancy checks, input and output validity checking, retries and restarts can increase reliability. And failure detection coverage. System RAM characteristics should be continuously evaluated as the design progresses, where system failure rates are not known, as is often the case for unique or custom developed components, assemblies, or software. Developmental testing may be undertaken to assess the reliability of custom developed components. The evaluations based on quantitative analysis assess the numerical reliability and availability of the system and are usually based on reliability block diagrams, fault trees, Markov models, and Petri nets. Markov models and Petri nets are of particular value for computer-based systems that use redundancy. Evaluations based on qualitative analysis assess vulnerabilities to single points of failure, containment, recovery, and maintainability. Primary qualitative methods are the failure mode effects and criticality analysis, FMECA. The development program discrepancy reporting, DR, or FRACAS should also be used to identify failure modes, which may not have been anticipated by the FMECA, and to identify common problems that can be corrected through an improved design or a development process. Analysis from related disciplines during design time also affect RAM. Human factor analysis are necessary to ensure that operators and maintainers can interact with the system in a manner that minimizes failures and the restoration times when they occur. There is also a strong link between RAM and cybersecurity in computer-based systems. On the one hand, defensive measures reduce the frequency of failures due to malicious events. On the other hand, devices such as firewalls, policy enforcement devices, and access authentication services, also known as directory servers, can also become single points of failure and performance bottlenecks that reduce system reliability and availability. Safety is a state of being certain that adverse effects will not be caused by some agent under defined conditions. Failure is inevitable for everything in the real world, and engineering systems are no exception. The impact of failures varies from minor inconvenience and comes to personal injury, significant economic loss, environmental impact, and deaths. Examples of major actions are Fukushima Daiichi nuclear disaster, Deepwater Horizon oil spill, Chernobyl accident, Bhopal gas tragedy, and Space Shuttle Columbia disaster. Causes of failure include bad engineering design, faulty manufacturing, inadequate testing, human error, poor maintenance, improper use of lack of protection against excessive stress. Designers, manufacturers, and end users strive to minimize the occurrence and the recurrence of failures. In order to minimize failures in engineering systems, it is essential to understand why and how failures occur. It is also important to know how often such failures may occur. Reliability deals with the failure concept, whereas the safety deals with the consequences after the failure. Inherent safety systems measures ensure the consequences of failures are minimal. Reliability and safety engineering provides a quantitative measure of performance, identifies important contributors, gives insights to improve system performance, such as how to reduce likelihood of failures and risky consequences, measures for recovery, and safety management. Need for higher reliability and safety is further emphasized by the following factors: increased product complexity, accelerated growth of the technology, competition in the market, public awareness or customer requirement, modern safety and liability laws, fast system failures, cost of failures, damages, and warranty. Safety considerations with undesirable consequences. Several definitions of risk exist in the literature. The most popular definition of risk is the one proposed by Kaplan and Garrick. They define risk as a function of answers to three basic questions: what can go wrong, how likely is it to go wrong, if it does go wrong, what are the consequences. Quantitatively, risk is defined as a set of triplets as shown in the equation. Risk is a function of S suffix I, P suffix I, X suffix I, where I is a scenario number, it varies from 1 to n, and S suffix I is an action scenario which has probability of P suffix I and the consequence of X suffix I. Risk and safety are related to each other. The higher the risk, the lower the safety. Risk assessment is also referred as safety assessment, with practically no difference in engineering applications. We are not God, hence nothing is absolutely safe, but we should strive to attain close to absolute safety. Safety should be built in the design itself. For example, if a pressure vessel fails with a safety valve in open condition, it is better than a failure occurring with a safety valve in closed condition. This concept is called fail-safe. Design parlance. Benefits of reliability engineering. Expectation. Products work under environmental and use conditions imposed by the customer. Creating a product that matches expectations imposed by the customer permits a product to work as expected. Understanding the conditions allows the design to meet without over designing, thus optimizing product cost and customer satisfaction time. Unanticipated failures cost time for customers and for the organization to resolve the failures. Using reliability and availability concepts, we can minimize failures and avoid wasting time. Throughput. Downtime for any reason reduces the system's throughput. Downtime can be minimized applying predictive and preventive maintenance programs. A well-maintained system minimizes operating expenses and maximizes throughput. Production. Some products require a run-in or burn-in to identify and eliminate early life failures or to refine and optimize system operation. Using reliability engineering techniques, we can minimize the time and resource impact of run-in or burn-in operations, eliminating or minimizing the time. We reduce inventory carrying costs, tooling costs, and energy requirements. Distribution, fewer failures, and optimized maintenance implies fewer spare parts in the logistics system. This minimizes the distribution cost, system costs for transportation, logistics, and storage of spare parts. This also minimizes service labor costs and service labor costs. Warranty, products that operate as expected without failure avoid being returned or serviced under warranty. Calls to service report, troubleshooting, product returns, failure analysis, and re-engineering are all part of the cost of unreliability or probability of failure. The warranty provides customers insurance in case of failure, and with reliability engineering techniques, the costs are minimized. Safety, some product failure cause unintended or unsafe conditions leading to loss of life or injury. Reliability engineering tools assist in identifying and minimizing safety risks. Product reliability, product failures can cause a loss of property. Minimizing failures and mitigating the damage caused by any failure minimizes exposure to liability for the property loss. Design, enhancing the design teams reliability engineering capabilities through training and staffing of reliability professionals enables the entire team to make decisions fully concerning the impact on product reliability. This reduces the need for expensive redesign or rework costs to address reliability related design errors. Now that all of you have watched this presentation so far, have a clear understanding of reliability, I have a $1 billion question for you. What is our reliability? Any guesses? Even medical doctors can never ascertain, even if they conduct all tests available. Reliability is a probability, but there is no point in saying that this person will live for 100 years with a probability of 0.005. It doesn't make sense. Doctors and hospitals charge so much for medical surgeries and allied expenses, but are they giving a warranty, if not guarantee, that this person will live for another 10 years without any similar ailments? All products we purchase, we ensure beforehand it is covered by warranty, guarantee, and all. But when it comes to precious life, we don't insist on similar terms. It's weird, Debates, discussion on open-ended topics like this can go on forever. Anyhow, let me pull the plug here. We'll meet again real soon with another interesting topic. Some of the statements, views expressed are solely mine based on limited knowledge gained over 6 decades of versatile experience. Always watch these videos with a closed caption for absolute 100% comprehension as per my sincere recommendation zillion times so far. I know I rushed to complete the presentation within 20 minutes max, which is a time limit I have set myself to retain the viewer's attention as a norm. I know nowadays I exceed this time limit since I make honest attempts to cover the selected topic more elaborately, including so many intricate fine details, referring a wide variety of sources. Nowadays I take twice or triple the time sometimes, depending on the presentation. I refer a wide variety of sources, in particular Wikipedia quite extensively, besides the articles and books published recently. I'm surprised by Wikipedia's coverage. It covers all the topics that you can think of it, but only thing is it is biased. Most of the things that they talk about are about things that have happened in US and all that. Besides, of course, I sprinkle my own salt and pepper and season it with my personal experiences so far in my life and also intuition. Stay at home as much as possible to maintain social distancing attributed to pandemic novel COVID-19 and prolong your lifespan. Lead a healthy life. God alone can put a stop to natural and unnatural events, maybe bio-war, cyber war, events like pandemics, which may lead to apocalypse and extinction of all sentient species on Earth for no fault of theirs. Rest in peace and harmony. Okay.